Through the movement simulation, a specific dynamic mechanism can be graphically analyzed. The figure shows some 2D dynamic mechanisms that can be simulated using solid face. Let's simulate a simple connecting rod crank mechanism using a simple rotation variable. In this case, the control variable and the variable that controls the rotation angle are the same. The rotational movement causes a horizontal translational displacement of the piston. See what the final design and simulation will look like. Let's design the mechanism. For the hand crank rotation, use a variable called ang. Let's create it with a value of 0. Create a circle with a radius of 40. And a straight line simulating the hand crank line from the center to any point on the circle. Select the hand crank line, and create a rotation command with the angle using the variable ang. Remember, if the variable hadn't already been created, we would be asked if we wanted to create it. Create the simulation command with the control variable ang and an initial value from 0 to 360 degrees. Note that the simulation command was stored at the end of the list. You can reposition it to the bottom of the list if you wish. This is not necessary because the simulation button searches for a save simulation command and runs the process. Create a double center line. And extend the horizontal line. Create the circle containing the connecting rod with a radius of 100. Its center will be positioned at the hand crank endpoint. Create the connecting rod line from the hand crank endpoint to the point of an intersection between the circle and the horizontal center line. Identify the straight line and then the circle. The construction of this line is the basis of the simulation. Create a horizontal straight line that simulates the piston. This straight line will start at the end of the connecting rod with a length of 80. Let's test the movement. Creating the piston with a radius or offset of 20. And horizontal mirroring. Joining the lines. Erase the reference circle used for the connecting rod construction and the piston baseline. Creating a center line. Testing. Remember that the hand crank line was created at a point on the circle between 0 and 90 degrees. In that position, it was easier to show the simulation geometry construction. Now, once constructed, edit the hand crank line so its endpoint ends in the circle quadrant with angle 0. The straight line will be rotated from its horizontal position. The ang variable is at 0 degrees, and this is the maximum position of the piston displacement. Create a vertical dimension. The maximum distance of the piston displacement from the vertical center line is 220. Create an offset of 222 to create the vertical line for the construction of the cylinder guide. Edit the ang variable to 180 to simulate the minimum piston displacement. Creating an offset line with 58. Create a dimension. Canceling dimensions. To build the cylinder guide, create two horizontal straight lines with offsets of 1 and 4. Select and join the vertical and horizontal lines. Create a section with hatches. Select the function outline attribute option and fill with hatches attribute with pattern 0. Select the outline again and create a vertical mirror. Edit the simulation and indicate the automatic loop option. Testing. Edit the offset to 3 to change the thickness to 2. Modify ang to 45. Save the file as drawing 2D movement simulation part 1. Repositioning the dimensions. Detailing the connecting rod. Creating two circles at the endpoints of the line. Joining the inner circles by two tangent lines. At the hand crank line, create two straight lines offset. We could also use two tangent lines, but because of the characteristic of this movement, it can result in positioning errors. Instead, using offsets, the system can handle the offset position better during the simulation. Note that a collision has occurred between the connecting rod and the piston guide. Edit the piston offset, changing the piston offset to 23. Add a fill with color to the construction of the connecting rod and piston. Select the circle and the tangent lines, and use the trim command to separate them. Erase the internal lines. Select and delete the lines to create a contour. Modify the fill attribute of the outline in the two inner circles with the default color option 0. Do the same fill operation for the piston. See that the two fillings have the same color because both were set with pattern 0. Let's place the piston with a pattern of 1 and choose another color. It is important to test the simulation during each phase of the process. One simple way to simulate the simple movement is to click on the base element that controls the simulation and test it by dragging the line. If any errors occur, you can edit the geometry directly on the graphics screen and then build a new geometry. But in parametric or simulation constructions, if it is necessary to rebuild the geometry, avoid deleting them through their selection in the graphics area. That is, avoid the erasure and then construction of new geometries. Both actions will be stored in the command list and cause an overhead during each reprocessing cycle. In other words, for each processing of the list, the geometry will be deleted and then a new one built. Instead, when possible, choose to delete the commands directly in the list of commands. This action will also force you to delete all subsequent commands and return to the original stage at that point. The inconvenience is that we can only delete the commands with errors and the following ones. That's why it's important to test each stage of construction. Therefore, if errors occur, a minimum of commands will be deleted to return the geometry to the desired intent. In Part 2, we will show how to retrieve geometric information from geometry and use logical conditions to create test messages.